So let's talk more generally about finite and algebraic extensions. Here's the setup. K over F is an extension, and you have A1, A2, An in the big field K. So you first need some notation. F round bracket A1, A2, An means the subfield of K generated by A1, A2, An. Meaning you have K, you have F contained in there, you have this bunch of elements in the big field. You throw them in with F and take the smallest field that it generates. So concretely, this would consist of all expressions like this. A multivariable polynomial expression in A1, A2, An, another multivariable polynomial expression in A1, A2, An, ratio of two such things, where F and G are polynomials in n variable. And the denominator is non-zero. So take a rational function in n variable and substitute A1, A2, An. Yeah, all such expressions. But if A1, A2, An are there, then any products and ratios will be there. So you get all these things, and this forms a field. Yeah, and I'll also denote by, so a special case of this, F round bracket A has already been introduced before. That's the subfield generated by F and a single element A. And then F square bracket A denotes the subring of K generated by A1, A2, An. So this concretely consists of all polynomial expressions, where F is a n variable polynomial. Yeah, so notice A1, A2, An are actually elements of K, whereas this x1, x2, xn are variables. And you could also say, now that we have learned the quotient field construction, that this field is the fraction field of that ring, or the quotient field of that ring. Okay, at any rate, so here's the theorem that we want to prove. It says, it basically gives a complete characterization of finite extensions. It says that finite extensions are those that you can obtain by adding finitely many algebraic elements, all together or one at a time. So let me explain. So here's the more precise statement. K over F is finite extension if and only if there are finitely many elements in the big field, each of them algebraic over the smaller field. Remember, algebraic means that each aj satisfies some polynomial equation with coefficients in F. So there is A1, A2, An in K, each of them algebraic over F, such that K is obtained by adding them, meaning K is equal to the smallest subfield of K obtained by A1, A2, An, or we say K is generated over F by A1, A2, An. And then part C actually seems weaker on first sight, but it's actually equivalent. You just say that there exists A1, A2, An in K, such that K is F1, A2, An, and I'm not insisting that all of them are algebraic over F. I'm only insisting that when you add the jth guy, it's algebraic over the field that you get by adding the previous ones. So you consider the tower F, A1, A1, A2, etc. This leads up to K eventually, and all you're saying is that A1 is algebraic over F, and then this A2 is algebraic over the previous one, etc. Just saying that is equivalent. And so before we prove this thing, we need to recall a few results. The first is, I've recalled three theorems here. The first is that finite extensions are algebraic, that we know. Second is that if you have a tower of extension F contained in K contained in M, then the degree of the big extension is the product of the degrees of the small extensions. This in particular implies that if the smaller extensions, if this one and that one are finite, then the big extension is also finite. And the third one, so these two we have done a while ago. The third one is basically something that follows from all the discussion about minimal polynomial that we had. And this is essentially a special case of our theorem, if you think about it, for the case when there is only a single element. Rather than a1, a2, an, we have a single a. So suppose k over f is an extension and you have one algebraic element, and you look at the field obtained by adding that single element, f parenthesis a. Then we have a description of this extension. This one we studied in great detail in the previous discussions. F round bracket a is isomorphic, we know, to the polynomial ring modulo the ideal generated by minimal polynomial of a. So there is a non-zero unique monic polynomial that a satisfies, and if you take the ideal generated by it and quotient out by that, that field is isomorphic to f round bracket a. In particular, what follows from there is that this extension has finite degree. In fact, its degree is equal to the degree of the minimal polynomial. So when you add one algebraic element, the extension that you get is always finite. Okay. Armed with all that, let's go through the proof quickly. A implies B. So I know K over F is finite. So let A1, A2, An be a basis for K as a vector space over F. If it's a finite extension, it's a finite dimensional vector space, so it has a finite basis. So you take these elements. Now, since finite extensions are algebraic, you see we are assuming it's finite, and theorem 1 implies, so theorem 1 implies each aj is algebraic over f, so they satisfy some polynomial equation. And of course, I will say of course here, even though you don't want to use this word often, but here it's warranted, I suppose. Of course, K is obtained by adding A1, A2, An. Remember what this means. This consists of all polynomial, or rather rational function expressions in A1, A2, An. You don't need polynomials or rational functions to get K. You just need linear combinations with coefficients in F, because they're actually vector space bases, which is a lot more than saying that. So these elements actually generate K as a F vector space, which is saying a lot more than saying that they generate it as a field. All right. So that's A implies B, and B implies C is sort of automatic. B is saying more than C after all. You see, B is saying that there exists A1, A2, An in K, such that each of them are algebraic over F, and K can be obtained by adding them. Now you just take the corresponding tower. I had that tower a little bit. So if you know B, you know that A1 is algebraic over F, A2 is algebraic over F, A3 is algebraic over F, etc. And eventually the last one is K. That's what B tells you. But if A2 is algebraic over F, then A2 is, of course, algebraic over this bigger field also. What does it mean to say that A2 is algebraic over F? It means that it satisfies some polynomial with coefficients in F. So A2 satisfies some polynomial for some P in coefficients in F and non-zero polynomial. But this field is contained in that field. F is contained in FA1. So any polynomial with coefficients in f is certainly a polynomial with coefficients in fa1. So this same polynomial can be considered a polynomial with coefficients in fa1. What I'm saying is, like a polynomial with rational coefficients is, after all, a polynomial with real coefficients. So a bigger field is even better. So A2 is certainly algebraic over this bigger field. A3 is already algebraic over this, so A3 is certainly algebraic over the previous one, etc. And that's what C is saying. So B implies C is automatic. The meat of the argument is in C implies A, because C seems to be the weakest of the three statements. So let's assume C, which means this is what we are given. We are given a tower ending in K, each obtained by adding one element at a time, and we know that the elements we add are algebraic over the previous ones. A3 is algebraic over F, A1, A2, etc. So let me just again argue in this picture. This time I have to use this theorem 3. You see, each of these steps are obtained by adding one algebraic element at a time. And FA1, A2, after all, is same as FA1, A2. Is the field that you get by adding A2 to FA1. And this A2 is algebraic over FA1. Now by theorem 3, each of these steps are obtained by adding an algebraic element to the previous field. So each step is finite. Each step in the above tower is finite. In fact, I can tell you what the degrees are. This degree is equal to degree of the polynomial PA1, where PA1 is the minimal polynomial of A1 over F. This degree is degree PA2, where PA2 is the minimal polynomial of A2 over the previous field. At any rate, all these degrees are finite. So this is finite, and so on. But then theorem 2 implies that the whole thing is finite. Because when you have a tower of finite extensions, the degrees just multiply. See, right here. So the whole extension is finite. So what you get is that the big elements in the big field, in particular what you get out of it is 2, is statement B, which means that you only knew that A2 satisfied a polynomial over this one, and A3 satisfied a polynomial over this one, and A4 satisfied a polynomial over this one, and so on. But at the end of the day, you know that all elements of K satisfy a polynomial with coefficients in this very small field F, all the way down. So that's where the thrust of the theorem is. Okay. We'll get some corollaries out of this next time.